All right, welcome. We're taking a look at chapter 3.2, the derivative as a function. So we've been working on derivatives. We have calculated them at specific points. Again, we are finding the slope of the tangent line at that given spot. Now, the issue is that if we want to find the slope at multiple spots, it just becomes a lot of work, okay? So, for instance, here we have a function f of x equals x squared minus 10x plus 1. And I want to find the slope at all three of these spots. Right? A graph, as we talked about, would at least give us a good estimation. So that's something we could do. But if we actually want to find it exactly, we'd have to do that formula 3 separate times. Well, what we can do instead is just leave, instead of putting the a in here, like we did in the past, and doing f of a plus h minus f of a, we can leave it as an x, right? And we can just do the derivative, do that limit definition of a derivative, leaving x in the equation, and then we can kind of change the x to be whatever we want to later, okay? So here's what I mean. So the limit definition of a derivative with that h function, if you try to do it with the x minus a version, the difference quotient, I'm sorry, that's the difference quotient. If you try to do it with more of the average rate of change formula, it's just not as nice and easy. So usually we do the h formula. All right, well, let's just see what we got. So inside of the f function, we have to put x plus h. So the limit as h approaches 0 of x plus h squared minus 10 times x plus h plus 1 minus the original function over h. All right, so again, this is a method that just requires a lot of multiplications. Okay, so depending on how well we remember how to do this stuff, I'm going to kind of go quickly through it. All right, so this first thing, x plus h squared would be x squared. X times h would be xh, but h times x is hx, xh. So this would be 2xh plus h squared minus 10x minus 10h plus 1 minus, let's distribute this negative, x squared plus 10x minus 1. All right, when you do this and you do it correctly, everything should kind of cancel out pretty nicely, okay? All of the things that don't have h's should go away. So like this minus 10x, this plus 10x, this minus x squared, this plus x squared, this plus 1, this minus 1. So everything that's left has an h value. That's really nice. So the things that have h, we can now reduce. The only things left has an h, has an h, has an h. So it'll be 2x, that h will cancel, plus h, instead of squared, it'll just be an h, minus 10. And we're doing this as h approaches 0. So now I can make h 0. It's totally fine. It's not in the denominator anymore, so we can do that. All right. So this is just 2x minus 10. All right, so our derivative, our f prime, is 2x minus 10. All right, and the nice thing is that that derivative is a function still. All right, we can put whatever numbers we want to into that function, and we can now find the slope of our function, of our original function, at any point, not just at a given specific spot. So now we can use this thing and evaluate 3 different ones all very quickly. 2 times negative 1 minus 10 is negative 12. All right, so now we can just plug in 2 times 0 minus 10, negative 10. 2 times 5 is 10, minus 10 is 0. All right, so our function is negative first slope, and then 0 first slope. Remember, the 0 slopes were the ones that we liked. And if we want to, we can check this out in our graph. x squared minus 10x plus 1. And, just kind of have an idea. So at -1, about here, would you agree that we have a very strong negative slope? Yeah, absolutely. At 0, a very steep negative slope. Yep, absolutely. At 5, I guess we'll have to change our window. Oh, that's not what I wanted to change. Not far enough. Sorry. All right, so just seeing farther down the graph, at x equals 1, 2, 3, 4, 5, would you agree that we have a slope of 0? Well, yes, I hope you will. All right, so our graph matches our results from our function. That's good. And now the nice thing is, again, we have an equation for our derivative instead of just finding individual numbers every single time. All right, so it allows us to just have an entire equation. And that's really, really, really nice for us. Again, the more complicated the problem, the more complicated the result. So it can just get a little tough. So for this h function, it's a cubic equation, so it's going to get a little tough. So we're doing the limit as h approaches 0. All right, we do h of x plus h So we put h into our, x plus h in for every x value. We subtract the original function, and we divide by h. So again, we can't just plug in 0 right now for our h. We'd wind up dividing by 0. We can't do that. All right, so we have to try to simplify. All right, x plus h cubed. All right, that is x cubed plus 2xh plus 2x squared h plus 2xh squared plus h cubed. That's how you cube something. I don't know if you know that, but we can do that. Minus 3x plus 3h minus 3h, sorry. Again, sorry, I skipped some of the algebra for this. You could write it out 3 times and multiply them together. Minus x cubed plus 3x over h. All right, and now good things should cancel. X cubed cancels with x cubed. Plus 3x and the minus 3x. And I think that's all it cancels. Notice everything that's left has an h. So the h can reduce in each one. 2x squared h becomes just 2x squared. 2xh squared becomes 2xh. h squared minus 3. Now we do the limit as h approaches 0. Since it's not dividing by h anymore, it reduced out. Let's see, this will go away, this will go away. So we just have 2x squared minus 3. All right, and then we can evaluate this at 3 different spots, very quick and easy. 2 times -1 squared, that's 1 times 2 is 2, minus 3 is -1. At 0, we get -3. 2 times 0 minus 3, -3. At 5, x squared, that'd be 25 times 2, that's 50. 50 minus 3, 47. All right, so we can do that, and we can have those. Okay. All right, to the third one. Square roots are always fun. All right, the rule we learned with square roots when we were doing the limits earlier is you multiply by the conjugate. So if it's minus in the middle here, I'm going to multiply by something with a plus in the middle. If you multiply it by the top, you have to multiply it by the bottom. All right, on the top, good things will happen. This times this will just be x plus h. This times that, so the square root of x plus h times the square root of x is the square root of x times the square root of x plus h. But when you do negative x, square root of x times this, those will cancel. All right, and then negative square root of x times the square root of x is minus x. The bottom we're just going to leave. We should notice that the x's here cancel. You see h and h will also cancel. But when something cancels from top and the bottom, we are left with a 1 on the top. It can't be nothing. So we still have a 1. And then now as h approaches 0, that's just 0 here. So 0 plus x is still x. So on the bottom, we have the square root of x plus the square root of x. Well, that's the square root, or 2 square root of x. All right, so that is our derivative here. And we can evaluate it. Putting in 1. Square root of 1 is 1, so this is 1/2. Putting in 4, square root of 4 is 2. 2 times 2 is 4. 0, put in 0 here, square root of 0 is 0. 0 times 2 is 0. So this is undefined. And putting in negative is also undefined. All right, so that's a good one to take a look at. We have the square root of x. All right, so the slope at 1, yeah, I can rationalize that would be a good 1/2 maybe. It's definitely positive. The slope at 4, 1, 2, 3, 4, yep, looks a little flatter than it did here. The slope at 0, now that's the weird one. So if we zoom in when x is equal to 0, the idea is right here, there would be no limit value. We don't have something to the left of 0. So the general idea is that the function is questionably continuous when x is equal to 0. So we can't quite do that derivative there. We can only do the derivative at a point kind of in the middle of our function. All right. Since this right here is not defined on the left side, we can't have a limit. And then also at -4, I mean, our function is not defined at -4, so there's no way to have a limit at -4. All right, notations. So sometimes you'll just see these other things. We've used f prime for derivatives, but we can write it as y prime. Remember, f of x is the same as y. You'll sometimes see dy dx, all right, the derivative of y with respect to x, or the derivative with respect to x of a function. All 4 of these things mean the same exact idea. Usually it's just the context of the problem that might change which one we use. Again, they all mean the same thing. And they all result from that idea of a slope. Okay, so we're doing the change in y, delta y, over the change in x, delta x, as that change in x becomes 0. Okay, so we want to figure out how the y values change as the x values change at a very, very small rate. All right, so once we calculate derivatives, we can leave them as functions, and we can graph those functions. So that's kind of something kind of useful. So I've got the graph of g of x pulled up. So let's just take a look at that. All right, so that was the graph of g of x. Let's look at the graph of its derivative, 1 over 2 squared of x. All right, so our graph and its derivative at the same time. right, so notice the two kind of work together. All right, important things kind of happen as we look at these things. Notice the derivative only starts kind of where the function itself started, so that's great. Let's see, and it slopes. Okay, so the graph of the derivative, the red line for me, is the slope of this thing at any given spot. So where it gets kind of weird, all right, we're not ever really going to look for where the two are equal. That's not really something that we care about, where a derivative equals the normal function. We kind of have to look at this as, just thinking of slopes. Okay, so this graph is just the constant slope of this thing. So the farther and farther we go, notice the slope is getting closer and closer to zero. All right, the farther you move to the right of a square root, it doesn't really look like it grows all that much. It is growing, it is getting taller, but it grows very, very slowly as you move to the right. Okay, but notice this derivative function is always above the x-axis. All right, it is always going to produce a positive value. Okay, all of these y values in our table for our derivative, no matter how far you go, these y values will be positive numbers. They'll be very small, but they'll be positive numbers, meaning that our function, our original function, is always increasing. All right, if the derivative is positive, that means the slope is increasing, which means that the slope is positive, so the function is increasing. Now, this will make a little bit more sense if we look at the graph of the other one. So let's see, maybe a Desmos graph will do us a little bit more good. X squared 10x plus 1. And then our derivative. All right, so the idea. Notice the derivative here, all right, at x equals 5. The derivative, if you remember, was 0, okay? So the derivative was 0, and that is the exact spot where our function changes directions. Notice the derivative to the left of this. These y values are all negative numbers, all right? Our derivative produces negative slopes. So looking over here, notice all of these spots, the function has a negative slope at all these spots. The function is decreasing at all these things. Here, the derivative is now in the positives, all right? The derivative has a positive value. That means the slope is now positive and our function is increasing. Okay, so where the derivative is positive, produces positive y values, that means the function, these y values might be negative, but the function is increasing in value. All right, so let's take a look at that next one. So x cubed minus x, I think that's what it was. X cubed minus 3x and 2x squared minus 3. Okay, so again, the idea, original function, okay, and derivative 2x squared minus 3. All right, so key ideas that match up. All right, 3x squared, oh my gosh. All right, so some key things should match up. Our function right here, for instance, all right, that's a maximum. The slope of our original function should be 0. And look, the slope at x equals -1 is 0. All right, if it's also 0 here for our derivative, which means, again, we have a slope of 0 here. It's a minimum value. All right, from here to here, what is our function doing? See how our function is decreasing? It's going down at these spots. All right, from here to here, the function strictly decreases. Well, notice the value of the derivative is below the x-axis. Yes, it comes down and it comes back up, but it's always below the x-axis. That means the slope of our function is negative below the x-axis. The function slope is negative, decreasing for all these values. After you pass one, you see how our derivative is in the positives? Well, that means the slope at all of these numbers is positive. The slope is increasing. Over here, the derivative function is above the x-axis, which means our slope here is increasing. The function is going up. Its derivative is in the positives. Okay, so the function is going up. Yes, the function value might be negative, but its derivative value is positive. The graph was increasing during those spots. All right, so the relationship between a function and its derivative is tough to figure out sometimes. All right, but it does tell us some very important ideas. All right, so using that same idea, we can kind of know what we know about a function and create its graph a little bit. So if this is a function, f of x, we can kind of plot its derivative based on its function. So like here, we have a slope of 0. So that means our slope is here at 0. Here, again, we have a slope of 0. So our derivative would be 0. All right, here, our slope looks like it might be about positive 1. It's like up 1 over 1. That's what I'm seeing here. Here, our slope is negative. So it's probably in like the negative 1 range. Okay. Here, our slope is negative. So probably in like that negative 1 range. All right. So if I just kind of start to connect these points, we kind of have an idea of what our slope might look like. All right. Our derivative function might look like. All right. So you see how the graph of our derivative is positive for all these values from negative 2 to positive 3. Our derivative values are positive, meaning our graph here is increasing. Okay. Here, our derivative values are negative. Notice our graph is decreasing. Okay, so you might get asked to put this on or make a sign chart for our f prime. So from negative 2 to 3, our graph, our derivative was positive. So our function is increasing. From 3 to infinity, or I guess at least as far as we know, f of x is negative, therefore decreasing. So our derivative after negative 2 is negative, so f of x is decreasing. Okay. So our sign chart is these pieces in those intervals. And what it tells us is what our function, our f of x, is doing. Okay. All right. The last little piece. Oh, there's more. The next thing is that we can only do functions. We can only do derivatives on continuous functions. And so the idea is if we can find its derivative at a certain spot, then that means if we have a derivative, then the function is in fact continuous. Okay. So you can only do derivatives when a function is continuous. So I have a derivative, I know the function's continuous right there. All right, so that's what it means. If it's differentiable, if we have a derivative, if we have a slope, that means the function is continuous at that spot. but it doesn't necessarily work the other way around. All right. Just because it's continuous does not mean we have a derivative. Okay. Continuity does not imply differentiability. Okay. So for some functions, we can have a continuous function, but it's not going to have a derivative. For instance, the absolute value functions. Okay. The absolute value at -3 of f of x plus 3. All right, if we try to do this using a table, so we need h values as h approaches 0, so we want like -0.1, -0.01. Those are negatives on the left. And then the right side would be like positive 0.1, positive 0.01. All right, so if we put these in for h, so we're doing our fraction, an absolute value of, we know our x is actually -3. So -3 that's not going to work. Plus 3 plus our h, and then -3 plus 3 would be 0 over -0.1. Right, if we repeat this with -0.01, we get -1. All right, so the derivative on the left side of -3 is -1. Derivative on the right side, so I just need to really get rid of these negatives. Is +1. And +1. So the limit on the left is -1. The limit on the right is +1. So overall, our limit does not exist. The idea is that a square, not a square root, an absolute value function all right, at that sharp point, all right, the bottom of the v, it does not have a derivative. All right, the slope on the right side we can find, the slope on the left side we can find, but immediately at that spot, you cannot take the derivative. All right, what is happening right here? We don't know. The slope was negative here, the slope was positive here. What's going on right at that v point? We do not have a derivative. Okay, so those sharp corners of a function, you cannot find their derivatives. Okay. Now, also, cube roots get a little weird. We can do this cube root, find the derivative at 0. The algebra function using that, actually the average rate of change formula will be very easy with this one. So the limit as x approaches 0, all right, we're doing it when x is 0, of this function. So we put in 0 for our a's, if that sounds familiar. Well, it'll be the limit as x approaches 0 of just the cube root over x. I hope you remember that the cube root is the 1/3 power. The square root is the 1/2 power. I hope these things come back to your memory. We use them a lot. And that allows us to say, hey, I can do this. The 1/3 power minus 1, these two things have the same base, so we can subtract their exponents. So this would be x to the negative 2/3 power. That's 1 over the cube root of x squared. All right, so now if we try to plug in 0, we're going to get that error message. All right, you can't do 1 divided by 0. Now it's the same idea for this one. The cube root, all right, so the 1/3 power. Look at what happens at 0. What would be the slope of our tangent line right here? Well, it's like perfectly vertical as x approaches 0. It gets like absolutely perfectly vertical. Vertical lines have an undefined slope. It's like something over 0. Right? And so that's the kind of issue. We can do the derivative. We can find the slope here. We can find the slope here. But right here at 0, we get that vertical line for a tangent line. And that has an undefined slope. We can't do that. So the function is continuous. It has values everywhere. But its derivative is not continuous there. All right. So if we call this f of x, actually our Desmos does a great job of being able to graph derivatives and functions. We can find the derivative. We can find the derivative. But right here at 0, that derivative is like a vertical asymptote. It does not have a value. All right. So in general, we can't find the derivative of a few types of functions. If you ever have a sharp corner, you can't find the derivative at that sharp corner. You can't find vertical tangent lines, vertical slopes. And then these things that get really, really weird at a certain spot. Like I can find the slope of like this thing as it gets closer, but right here at this spot, we cannot find the derivative at that really weird spot. I can find the limit of the function itself. The function itself is going to 0, but its derivative, what the graph is doing, its slope, we can't do that. All right, so derivatives, we can find a lot of them, but derivatives struggle at these three kind of ideas. Okay, the limit of the function itself is very doable, but the derivative of that function is not. All right, and so you can find higher order derivatives. This is our last thing. You can find the first derivative. You can even find the second. You can take the derivative of the derivative, or the third, the derivative of the derivative of the derivative, or the fourth. Notice when you go to the fourth, we stop using these little apostrophes, and we just say in parentheses the fourth. So that means the fourth derivative. So the fifth would be a little 5 there. Notation-wise, you might see like the second derivative of y of x, the dx squared. It comes from this notation. We're taking derivative of a derivative. And then on the bottom, it's the derivative with respect to that. So the notation gets a little weird. But in general, first derivative, second, third, fourth, we use that notation the most. We use this notation probably the least. We never use this notation. But the other thing that we do kind of talk about as we progress with our derivatives, the position of a function is just position of an object can just be a function. The velocity, aka speed of a function, is the first derivative. And we're going to talk about that a lot as we go forward. And so the acceleration of a function is going to be given by the second derivative. We're going to use these three ideas a lot. So as we're doing things, these three words are going to come up a lot. I like to think about it as if I'm driving a car. All right. If I'm driving a car, my car itself has a position. I'm so many miles away from my house, okay, for instance. And I have a speed, all right? My speedometer tells me that speed, okay? So if I'm moving forward, my speed is positive. That's great. If I'm, in reverse, my speed is negative, okay? And we have that idea. Now, acceleration is how is the speed changing? Okay, so my car is on the road, I have a position. My car is moving, so maybe my foot is on the gas pedal. All right. Now, my foot being on the gas pedal just means I have a speed. Okay. Now, am I pushing the gas pedal to make my speed go faster? Is my speedometer, just here? Or is my speedometer moving forward? All right. If my speedometer is just staying still, my acceleration is 0. But am I pushing down on that gas pedal? Is my speedometer increasing? Is my speed increasing? Then my acceleration is increasing. Am I letting off the gas pedal a little bit? Am I trying to slow down? So my speed might be decreasing because my acceleration is also decreasing. Okay. So position where I am, my speed is my foot on the gas pedal. My acceleration, am I pushing down on the gas pedal? Am I lifting up on the gas pedal? Or am I keeping that gas pedal exactly where it is? Kind of that idea. We use that a lot. All right, and then we can do this. We can do some derivatives of derivatives. So we already found h prime. We did that example. So to find h double prime, the second derivative, we have to do that formula again. The limit as h approaches 0. All right, we put x plus h where our x is. There's no x here, so that's just 3. Subtract the original function. All right, this thing, x plus h squared, I have to do that first. That would be x squared plus 2xh plus h squared. I see our 3's cancel right away. That's nice. We can distribute that 3, and the 3x squared and the minus 3x squared, those will cancel. So I'm doing this fast. So 6xh plus 3h squared over h. All right, and so this derivative, these h's will cancel. And now as h approaches 0, we just get 6x. So 6x would be our second derivative. Our third derivative, six x plus h minus 6x over h. Well, this one's really easy. 6x, 6h minus 6x. So that's just 6h over h. That's just 6. Our fourth derivative, there's nothing to plug in, so it's just 6 minus 6 over h. Well, 0 over h, 0 over anything is going to be 0. All right, just remember, h isn't actually equal to 0, but just really close. So 0 divided by something is going to be 0. All right, so in general, what we kind of learn is that the derivative of any constant is 0, and then, derivative of 0 will always be 0. All right, so we can find higher order derivatives. They just take some more.